Hi. So in this class, we'll be talking about modular arithmetic. This is fourth class of our number theory course. So let's just get started with this. Here, we'll first define what it means to say that two integers are congruent to each other. And the definition of congruency is this. For any integer n, we can say that A is congruent to B mod n if n divides A minus B. So here A and B are integers. So basically you can say that any two integers A and B are said to be congruent modulo n. This is called like A is congruent to B modulo n. Modulo n if n divides A minus B. Basically, you can say that A is equal to n times some quotient plus B, right? So A minus B is equal to n times some quotient. So A minus B is completely divisible by n. A minus B is completely divisible by n. Also think of B as the remainder when you divide A by n. When you divide A by n. So that is the meaning of this congruency. And we'll see how congruency is very powerful and can be used to solve many types of problems. So first, we'll add another definition. This is the definition of a residue class. Now, what is this residue class? Residue actually stands for remainder. So residue class is the set of all possible remainders when you divide two integers. So let's define this. Pick a natural number n. Pick a natural number n and a non-negative number r which is less than n. Number r which is less than n. Then the rth residue class of n. Rth residue class of n is the set of integers a that satisfy a is congruent to r mod n. Basically, this means the set of all integers that leave remainder r when divided by n. So if you take any number that gives a remainder r when divided by n will belong to the rth residue class of n, right? So the numbers here would be things like r minus 2n, r minus n, r plus n, r plus 2n, and so on. And this residue class is basically an infinite set. There, all of these numbers, if you divide by n, you will get r as a remainder, right? We are just adding some multiples of n, either positive multiples of n or negative multiples of n, right? So now let's look at some of the properties that come from these definitions. So the first properties is if A is congruent to R mod n and B is congruent to S mod n, then we can say that A plus B is congruent to R plus S mod n. Okay, so We can just take some numbers and see whether it is true. So let's say 5 is congruent to 2 mod 3, and let's say 12 is congruent to 1 mod 11, right? Now, actually, we had to take the same mod. So 12 is congruent to 0 mod 3, actually. We can take another number. 11 is congruent to 2 mod 3, right? So 5 plus 11, 16 should be congruent to 4 mod 3, which is equal to 1 mod 3, right? So you're getting 2 plus 2, 4 mod 3, which is also 1 mod 3. 16 is 1 mod 3 because when you divide 16 by 3, you get remainder 1, right? This is the first one. The second property would be A into B is congruent to R into S mod n. And another property is A is congruent to B mod n implies, this implies that A plus C is congruent to B plus C mod n. It also implies AC is congruent to BC mod n. So you can multiply and add any number to both sides of a congruency and the congruency remains the same. You can even add a power. A power C is also congruent to B power C mod n, right? So when you have a congruency like this, you can manipulate it by adding any constant number to both sides. Also, you can multiply a constant number and raise it to a constant power, right? So these are important properties of congruencies that you should be aware of. The next thing is, what about division? Division is something that you have to be a little careful when you handle congruencies. So if you have Ka is congruent to Kb mod n, now this implies you can divide K out and say A is congruent to B mod n, but only under certain conditions, only when GCD of K and N is equal to 1. You cannot do it if there is common factor between N and K, right? N and K basically have to be co-prime. Then you can divide by a constant number. So use this, but be careful when it is applicable. It is only applicable when K and N are co-prime. Only then can you divide a number on both sides of a congruency. Now let's use these properties to check out some questions. So for example, find the last digit of 9 power 1003 minus 7 power 902 plus 3 power 801. So if you want to find out the last digit of any number, it is basically finding out what is that number mod of 10, right? What is the remainder when you do divide that number by 10, right? So why don't you just do modulus of each of these with respect to 10? Excuse me. So if you think about it, 9 power 1003 is the same congruent to minus 1 power 1003 modulus of 10, right? Because 9 is congruent to minus 1 mod 10. So it becomes minus 1 mod 10, because minus 1 power 1003 is minus 1, which is same as 9 mod 10. Because saying that the remainder is minus 1 means saying that the remainder is also 9 if you divide by 10, right? Similarly, 7 power 902 will be congruent to, it is the same as 49 power 451, and that is the same as, again, minus 1 power 451, because minus 1 comes here. Last digit is 9, so minus 1 power 451, it is same as 9 mod 10 again. And 3 power 801, 3 power 801 will be equal to 3 into 3 power 4 into 200, which is 3 power 81 power 200, which is 1 power 200. So it is congruent to 3 mod 10, right? Because 81 has a remainder of 1 when you divide by 10. So 1 power 200 is congruent to. So this is 3 mod 10, which is last digit is 3 here. So if you add up all of these numbers, actually you have to subtract the first two. So 9 minus 9 will get 0 plus 3. So the last digit of this will be 3. Because you can combine now each of those numbers. It is 9 mod 10 minus 9 mod 10 plus 3 mod 10. So last digit will be 3 here, right? Let's do another question which is similar. Find the remainder when find the remainder when 3 power 89 is divided by 7. 3 power 89 is divided by 7, right? So we can say that 3 power 3 is 27 is equal to minus 1 mod 7, right? So 3 power 3 is minus 1 mod 7. We also have 3 square is 2 mod 7. And if you look at it, 3 power 5 is 243, which is equal to minus 2 mod 7, because 243 245 is divisible by 7, it will be 35, and 245 is divisible by 7, 243 is minus 2 mod 7, so this is equal to just 5 mod 7, right? So now let's look at 3 power 89. It can be written as 3 power 84 into 3 power 5, which is equal to 3 power 3 power 28 into 3 power 5. And now 3 power 3 we know is minus 1 mod 7. So it is minus 1 power 28. And 3 power 5 is 5 mod 7, right? So the overall thing comes out to be 5 mod 7, right? Because this becomes 1 mod 7 and this is 5 mod 7. So very quickly you can find remainders when you apply congruencies to problems, right? Now, let's look at some extensions of this theory of residues and residue classes. So we have a theorem here which says, let P be a prime number, let P be a prime number, and consider the set S to be 1, 2 till P minus 1, right? This is the set of, consider the set S to be set of remainders modulo P. So whenever you divide any other integer by P, these are the possible remainders that you might get, right? Non-zero remainders. Unless the number is divisible by P. If the number is divisible by P, obviously you'll get 0. But otherwise, these are the possible remainders that you can get. 1, 2 till P minus 1. Let A be any integer, co-prime to P. Co-prime to P. So basically A and P have no common factors, right? Then we have A times S is congruent to S mod P. So AS means, basically the set obtained the set obtained on multiplying each element of S, each element of S by A, right? Okay. And AS is congruent to S mod P. So let's take an example and try to understand what this really means. So if we choose P to be 5, let's say P is supposed to be a prime number, P is 5, then my set S is what? Set S is 1, 2, 3, and 4, right? Let's choose another number which is co-prime to 5. We can choose any number which is co-prime to 5. So let's say A is equal to 8, right? 8 is co-prime to 5. There's no common factors. So except 1. So if A is 8, A times S. A times S, what is the set of A times S? So multiply each element of the S set by 8. So it will be 8, 16, 24, and 32, right? Now, if I take modulo P in these, modulo 5 here, let's see what we get in these elements. So notice that this becomes 3, 1, 4, and 2, right? Modulo P. Now, our S set was what? S set was 1, 2, 3, 4, right? AS set is becoming what? It is becoming 3, 1, 4, 2, right? So the fact is that AS set is just another arrangement of the elements of the set S. So the order may be different, but the same elements are coming and the same number of elements are also present. So AS is congruent to S modulo P as long as you have P is a prime and A is a integer which is co-prime to P, right? And what was S? S was the set of possible remainders that you get when you divide any number by P. So we will use this property that AS is congruent to S mod P to now prove Fermat's little theorem, right? So Fermat's little theorem, let's think about this one. So the statement of the theorem says that if A is any number, if A is any number co-prime to P, co-prime to P, where P is a prime, then A power P minus 1 is congruent to 1 mod P. That is the statement of the theorem. Now, how do we prove this? It is very easy actually. So what is the set S for P? It is the set of 1, 2, 3 till P minus 1, right? So if we construct the set AS, right? AS set would be A, 2A, 3A, and P minus 1A. Now we know that AS is congruent to S mod P, right? From the previous theorem. So what we will do is multiply each element of this AS set. Now each element of this AS set is actually congruent to some particular element here, right? There is a connection. All of these elements correspond to each element here corresponds to one element here, right? So if we multiply, the result will still remain congruent, right? Because if two numbers are congruent to each other, then multiplication will still remain congruent, right? So what we will say is, multiply all of these. We'll say A into 2A into 3A into P minus 1 into A. It should be congruent to 1 into 2 into 3 into P minus 1, right? And whole thing is mod of P, correct? So here we have P minus 1 elements. So you can quickly get A power P minus 1 into P minus 1 factorial should be congruent to P minus 1 factorial mod P. Now, if you remember, we discussed when we can divide both sides of a congruency by an integer, right? So we had the property that if you have Ka is congruent to KB mod n, then we can write A is congruent to B mod n as long as GCD of K and n is equal to 1, right? So here we can divide by p minus 1 factorial on both sides and cancel this p minus 1 factorial from here and here, as long as we are sure that p minus 1 factorial GCD with p is equal to 1. But that is true because p is a prime number and p minus 1 factorial will be all the integers which are less than p, basically till p minus 1, all the product of all the integers less than p, and there is no factor for p which is lesser than p, right? Because p is a prime. So GCD of the p minus 1 factorial with p must be 1. Therefore, we are able to divide this congruence. And once you can divide this congruence like this, you will get Fermat's little theorem, right? So Fermat's little theorem is actually very important because it is one of the good checks for whether P is a prime or not. So you can always say that if P was a prime, then it must satisfy this relation where you take A as any number co-prime to P and you raise it to the power P minus 1, it should give you a remainder of 1 mod P, right? So that is your Fermat's little theorem. Now, in the next video, what we'll be talking about is inverses and the existence of inverses. And we'll also do Wilson's theorem in the next class. So stay tuned. We'll continue with the course in the next few videos and we'll finish the theory part for number theory soon. See you next time.